Hey everyone and welcome to this video. In this video, I'm going to talk about the mathematics for machine learning, linear algebra, where I'll be talking about everything you need to know about linear algebra. One of the most demanded video on my YouTube comments, on my LinkedIn messaging. Hey Ayush, can you make a video on mathematics for machine learning? So here it is. So it is a bit long video, but it covers every mathematics prerequisites for the ML001 course that I recently launched, which is machine learning in depth courseware. So this video will cover everything you need to know about linear algebra that is required for machine learning. Okay, so it is for both machine learning as well as for deep learning. So if you cover this video, then you're good to go with machine learning as well as with deep learning. But in deep learning, I'll be covering one more video or two more videos for statistical and probability as well as numerical optimization. Okay, so but you don't need that two videos for machine learning. However, you can also watch that. But for machine learning, you don't need that two videos. But still, I will put so that it covers the prerequisite of my deep learning course, which is coming. Okay, so this is the basic intuition about this video. So why this video was most awaited? Because I just posted, hey, what do you want? All were saying, hey Ayush, bring mathematics for machine learning. Hey Ayush, bring mathematics for machine learning. So it took me a little bit long because I was making a detailed content of this, doing a lot of research. Either I have put just seeing what are the main concepts, just writing some examples, because when I write any notes of mathematics, I make my own examples. I try to get into depth into that for my learning as well. So I'm gonna do it. Took me a little bit long to prepare for linear algebra, but I'm back with linear algebra, and I hope that those who are comfortable with this mathematics for machine learning, they are good to go with my ML001 machine learning in depth course. And I'm with my favorite whiteboard and with my dictionary. So if I forgot any kind of English, I'll be very happy to take a look at my dictionary. So it just works fine for me. So I am with my dictionary as well as I'm with my whiteboard. Sorry, it's a blackboard, and I'm with my notes. Okay, so these are my notes, which are my personal notes that I prepared, but I don't give to this anyone. This is in a pink paper, but still, if someone wants me, definitely I will think about it. Okay, so let's start. And if I do any kind of English mistakes, please be sure to just ping me up in the comment. Okay, let's start without wasting time. So the first thing first, let me tell you what we are going to study in this video. In this video, we are going to talk about scalars, matrices, vectors, properties of matrices, operations with matrices. Let me see, norms. We will see the dot product. We'll see the orthogonality, inner product, and then we will see the two kind of matrix, which is inverse and transpose of a matrix. Some of the norms we'll see, how do we take out the norms of a vector, matrices, and then I will go forward in singular value decomposition, eigenvector, eigenvalue, and etc. Okay, so this is just a basic high level overview of this video. So let's start with the first topic of this video, which is scalars, vectors, matrices. Okay, so first of all, what is scalars? It is given a new name, scalars. It is just a number. Okay, so what is scalars? Scalars, let me write 1.1, which is scalars, matrices, and vectors. Okay, so sorry, yeah, it's first of all I have to write vectors and then matrices, no worries. Okay, so for what is scalars? What is scalars? Scalars are just like numbers. So I will tell you, it's just given a fancy name in terms of linear algebra. It's just like numbers. So sorry, I haven't written for a long time on the board, so I have to fit my hand. Scalars are just like numbers. Are just like like numbers. For example, you can take scalars as 4. This is a scalar. These are just a simple number. So this is a scalar in terms of linear algebra. Okay, so we can think of it as a 4 as a scalar, we can think of it as a 5 as a scalar, and etc. Okay, so these are scalars, and how scalars are denoted? Scalars are denoted in italics form, in lower form. Okay, what is this? So you denote the scalar. For example, you denote this 4 as in italic form. You store it into a variable. Okay, so in italic form in lowercase equals to 4. So a here is a scalar. Okay, so in italic form, I'm not able to write italic, but in italic form and just say lowercase. So that's how we identify in general case scalars. Okay, so I hope that no further explanation is needed for scalars. It's just like numbers, which is 3, 4, 5, 6, 7. I hope that you already got this. Okay, so what are vectors? Vectors are like arrays of numbers. Okay, so arrays of numbers. So here's a good definition. Then I will give you some examples to help you better understand what are vectors and what are matrices. So 1.1.2, vectors are arrays of numbers. Vector are arrays of numbers. I will tell you, just don't be confused about this. I will talk very much about vectors over here. So it's written in bold. It is written in bold. It is written in bold. Okay, it is written in bold. Just lowercase and lowercase. So you write a V, which is in bold. Okay, V equals to your vector 1, 2, 3. Okay, so this is an example of a vector. So how do we identify this is a vector? Because it is a one-dimensional, I would say, matrix. It's also known as 1D matrix. 1D matrix. You will see what is matrix just in a second. But this is how you denote the vectors, and all the elements in that vector identify the points in a coordinate plane. So what do I mean with that? I am correct. Yeah, in coordinate plane. So for example, let's in physics, if you have come from physics, then you know about vectors. If you have come from linear algebra classes, then I think that you know about vectors. So for example, let's take an example of a vector 1 over 2. Okay, so this is our example vector. So I will just draw my favorite. I will just draw this one. I hope that everyone is able to see y and x plane. Okay, so x and y plane. Okay, so this is all obviously 0, this is 1, this is 2, this is 3, this is 4, this is 1, this is 2, this is 3. Okay, so here we can visualize this vector into this coordinate plane by plotting it out over here. So we can take this 1 as an x point and 2 as y. Okay, so this one and this one here this is our vector v. Okay, so this is our vector v, which is denoted like this, and I hope that you understood what a vector is. So in simple terms, vector are arrays of numbers. You will see how we use vectors, why we use vectors, etc. But vectors are in arrays of numbers. You can think of it as identifying points in a coordinate plane. Okay, so it is a 1D matrix with with one column and n number of rows. Okay, so that's we call 1D matrix. We call this as a 1D matrix, and n number of rows. It can have any number of rows. Okay, so each element can be identified on this. Okay, so just take it 1 by 2. You can see this is a vector v. Great. So we can see the more examples of vectors. So let's see another example of a vector A. Okay. So the vector A can be 2, 4, 8, 9. So we have here the number of rows. The number of rows is 4 and the number of a column is 1. Okay. So this is the shape of this vector, and basically we denote that the number of elements, these are called elements, 2, 4, 8, 9, these are called the elements, which are in the vector. Okay, so the size of this vector is 4, 1, which means that we have a total of 4 rows and 1 column, which is over here. Okay, so these vectors are a special type of matrices. Okay, so that's let's see what a matrix is now. So I have said it is a special type of matrices. So first of all, what are matrices? So this is also a good question to ask. So matrices are n-dimensional vectors. Okay, so matrices are n-dimensional vectors. So let's see how we can have any number of rows. It can be 2D array or 3D array, 4D array. Okay, so matrices are, it can have any number of columns, any number of rows. That's called matrices. So it is written in uppercase letters. So we write A, this is a matrix. Okay, so we write matrix as a 1, 4, 3, then 2, 1, 4, 6, 1, 9. So this is an example of a matrix where it has n-dimensional, it's m number of rows, m number of columns and n number of rows. Okay, m number of columns, and n number of rows. So the shape of this matrix is A equals to the we have 3 rows and we have 3 columns. Okay, so we usually denote rows as I and the columns as Z. Okay, so we have 3 by 3 matrix. So here we have 3 by 3 matrix. Okay, so this is how this is what a matrix is, and I hope that you are understanding what I'm trying to say you here. So matrices have m number of rows, m number of rows, and n number of columns and n number of rows, whereas a vector is a 1D matrix, which I mean that it has only 1 column and n number of rows. Okay, so that's why vectors are called the special matrices. Okay, so this is what a vectors and matrices are, and I hope that you understood what do I mean with matrices and what do I mean with vectors. Okay, great. So we had talked about vectors, what are scalars. So let's recapitulate so everything is on the same page. Scalars are just like numbers, which is represented by italic case with lowercase. For example, 4, 5, 6 are the scalars. Then we have vectors. Vectors are arrays of numbers. It is a special kind of matrix where it has a 1D column, 1 column and n number of rows. And then we have matrices. Matrices have m number of a column and n number of rows. Okay, great. So we had talked about the scalars, we have talked about this vectors, we have talked about this matrices. Now it's time to talk about some operations doing not with operations. So something called as transpose of a matrix or transpose of a vector, whatever you can say. So first of all, transpose of a matrix. So let me write the definition formulating over here. So what is transpose of a matrix? So basically many you will see in my videos on ML001 or whatever maybe machine learning course, mainly people do theta t. What is this? Theta transpose is doing the transpose because theta over here is the matrix, is a vector. Theta 0, theta 1, all the way down to the theta j, where we have a j is the number of features. So it is a vector. So you apply transpose over to this vector. Okay, so after applying the transpose to this vector, it will become at the mirror size. So like this, I will show you how it works. So it will be like theta 0 times theta 1 all the way down to theta j times x1 x2 all the way down to the x. Okay, so this is what they do. This is what do I mean with the transpose. But let's see the formal definition of a transpose, so that it makes sense. So it's just like the mirror image of your matrix across the, it's the mirror image. So what do I mean by mirrored image? It's just let me write the definition, then I will make you with the help of an example. So to transpose of a matrix, the transpose of a matrix or a vector is the mirror image of a matrix diagonal across the diagonal, called, it's also called the main diagonal. That's the diagonal is called the main diagonal, and running down from right, starting from the upper left. So now see that just is a mirror image. So for example, if with the help of an example, it will make sense. A equals to A11, A12, A21, A22, it's 3-1, so sorry, A32. Okay, so this is your basic matrix. For example, this is your matrix. Now you apply the transpose. So how you apply the transpose to this matrix? You just add A subscript T. So what it will do, it will do the mirror image. It will do the mirror image of the main diagonal. Okay, do the mirror image of the main diagonal, and the resulting matrix will be A11, A21 means this side like this, A21, A31, then A12, A22, and A32. That's the basic, that's how you do the transpose of a matrix. Okay, so this is how you done a transpose of a matrix. So what you have done, you've taken a matrix, okay, A, but you may think, yeah, what is this 2 1 2 1 subscript? I will tell you the how do we assess the elements of a matrix. Okay, so you apply a transpose to this A, and your transpose gives the A11, A21, A31, but because it's the mirror image of your diagonal. Okay, it's the mirror image of your diagonal, so it's 3-1 is just comes to this, and then the first in other words I could say the first column become the first row, second column because the second row. that's the basic thing. Or I could say taking this A11 is but in simple terms is the mirror image of the main diagonal which are here, so it's just the mirror image. You do this like this. Okay, so that's the basic transpose, what the transpose is, and it's basically used everywhere. Great. So first of all, how do we assess the elements of a matrix or a vector, because it's also an important concept to learn about. So for example, you have this vector A where we have some elements 5, 6, 7. Okay, so you are told to assess 7. How do you assess 7? For assessing 7, you will write A, and then for example, let's assume that start from 1. Okay, start from 1, then 2, then 3. So the I, so here we assume I as the which row, the index of that 7. Okay, so it's actually 3, A3. So 7 is located at this index. Okay, or I could say we can assess that element 7 using A subscript 3, where 3 denotes the row index or the row number. Okay, in that vector, and and we denote it as AI. So for assessing any elements of a vector, you write whatever the name of the vector, and the row index or the row number. Okay, and then you will be assessing your elements. Okay, so it was pretty much easy. So what about matrices? So for example, you have a matrix, just assume A, big A. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is your favorite matrices. So how do you assess this 5? Okay, how do you assess this 5? For assessing this 5, you don't have to do anything. You write A. First of all, you will identify which row. So it is in this is the first row, this is the second row, so this is in second row, and then which column. So it is in second column, first column and second column. A22, that represents 5. Okay, so you go here, and then you go at the top over here, and then you reach out to your element. Okay, so in general terms, for assessing the elements of a matrix, you write A, then what's the row number and what's the column number. Then you will assess your favorite element. Okay, so that's how you do. And that's the same way that I've done over here. A11, the first row, first column. A12, the first row, second column, the second row, first column, the second row, second column, the third row, first column, the third row, second column. So that's the thing. And then you apply your transpose. Is the mirror image of your main diagonal, and then you get the, after transposing, you get this number. Okay, great, pretty much clear till here. I think we are pretty much clear about this. Great. So for example, you can write your vector. You can write your vector as a transpose. What do you mean with that? So what do I mean with that is you can write your vector x equals to the x1, x2, x3, and x4. Now you tell me, is this a vector or a matrix? Okay. You tell me, is this a vector or a matrix? Just so you can comment it down below. I'll be very happy that someone has watched my video. So please comment it down below. I'll be very happy to see the comments. Is this a vector or a matrices? It is. Again, I'll let just two seconds more. So I have written x1, x2, and just assume that these are the elements. These are the elements of a vector. These are the elements of a vector. And is this a vector or a matrix? It is a matrix. It is a matrix. But wow, how it is a matrix? Because it has m number of rows and n number of columns and n number of rows. Because in matrix we haven't said it anything. We said you can have any number of columns, any number of rows. Okay, but in vector we have strict rule. We should have only one column and n number of rows, and that's why this is a matrix. But I can make this as a vector. How you can make? Just tell me how you can make this as a vector. Please comment down below again. Put a timestamp again because it will be a long video. So please put your timestamp below. So I'll be very happy to see how you can make this as a vector. What you can do? The intelligent people, what they will do? They will take this x2, x1, x2, x3, x4. Great, your answer will be correct, but using linear algebra options, means the operations. Okay, so what you can do, you can apply transpose over here. You can apply the transpose over here, you will get this. Okay, so when you apply your transpose, it will transpose your vector, sorry, a matrix, but it's in a vector. Okay, so this is special properties of these. Okay, so there are a lot more which you will see. Please follow some of the linear algebra cookbook if you have. But in this video, I will give you all the information that you need for ML001 or machine learning. Okay, so we had covered this, and something more can be there is one more property. These were the first property. There is one more property, is if you transpose your matrix A transpose given I and J, and I here is the row and J is the column, it will be equals to the A J I, where J is the column and I is the row. Okay, so these are the special properties of transpose. When you, just operations, just using the transpose. These are special things that arise. There are a lot more, but I'm not going to talk about that in this because whatever needed is here only. Okay, so transpose used a lot, so I've just talked about that, and I hope that you understood everything you need to know about transpose of a matrix. Okay, so I had covered my one page of notes. So now let's go to, so after completing the transpose, we have completed the scalars, matrices, vectors, we have completed transpose, and etc. Now let's talk about the operations with the matrices. Great. So operations with matrices. Operations with matrices. Okay. So this is the main topic now. So operations. So first operation that we will talk about is adding the matrix, or the addition of a matrices. So assume that you have a matrix A, and you have a matrix B. You want to add it. So when you add it, A plus B, it will result in C, of course. Okay, so here what you do the element wise adding. Okay, so you add Aij plus Bij equals to the Cij. Okay, so for example, okay, so the addition of a matrix is simply this one. For example, let's take this example, 1 by 3 plus this is your matrix A, this is your matrix B. So what do? 1 plus 4, 3 plus 1, 2 plus 2, 4, 3 plus 4, and you will get your resulting matrix 2 by 2 matrix. Okay, so this is how you do the addition of a matrix. Now, how do you do the multiplication of a matrix? So for multiplication of a matrix, so let me write where it is. Yeah, so the multiplication of a matrix. So for example, you have a matrix 1 by 3, 1, 3, 2, 4 times. You have a 2 by 2 matrix 5, 0, 6, 7. Okay, so if you are told to multiply these two matrices, what you will do, you will take this 1 by 2, and multiply with the first row, with the first column of the second matrix. Okay, let's do that. 1 by 5 plus 2 times 0. Okay, the second thing what you will do is this, you will take this 1 by 2, then you multiply with 6 and 7. Again the same thing, 1 by 2, and this now the second column, 1 times 5 plus 2 times 6. Okay, now you will take the second row and then multiply with the first row of the second matrix, 3 times 5 plus 4 times 0, 0. Then this now it's time for 4. Now this time for the second column is 3 times 6 plus 4 times 7. That's what the matrix multiplication is, and I hope that and then you add it all up over here, and you add it all over here, add it over here, add it over here, add it over here, means 1 times 5 plus 2 times 0, which is obviously 5. Then 1 times 5 plus 2 times 6, 5 times 5 plus 12, which is 13, 14, 15, 16, 17. Okay, you can write it down. So it's just some here, it's just some here, it's just some here. Okay, so this is a resulting matrix. Okay, so this is what your resulting matrix is, and it's a 2 by 2 matrix. Okay, So this is your favorite matrix multiplication. The second thing is something called as dot product, or sorry, it's not a dot product, it's a Hadamard product. Okay, so it's the Hadamard product is defined as a this signature B. So this is the Hadamard product. So dot and so now we'll see the dot product and Hadamard product. Okay, so the dot product is the element wise multiplication of a matrix. So but for this, your x and y should be of same shape. Okay, so for example 1 2 3 4, and if you take the dot product between 3 4 6 5, then what you will do, you will simply 1 times 3, 2 times 4, 3 times 6, 7 times 5. That's what you will get. Okay, so this is how you take the dot product, and the dot product is written by x dot y, and mainly in Python you can write np dot you write x and y. You want to take the dot product, you just do the element wise product, and then this is what it is doing. Okay, so we are done with this multiplication of matrix. For a little bit just the equation a little bit, but I hope that you understood what a dot product is and the multiplication of a matrix, etc. Okay, so here are some of the properties of a matrix. So for example, you can write it is associative. So sorry, it's a distributive. Matrix multiplication is distributive and associative, but it's not commutative. Okay, so a b plus c is ab plus ac. Okay, so this is distributive. We can also write associative, a b plus c, ab plus ac. So it's associative, it's distributive, but it's not commutative. If you multiply a times b is not equals to b times a. Okay, the results will be not same. Okay, you can try with some examples. Commutative. Okay, so these are upon you. If you are curious, you can apply these. Okay, so this is what you do, and but the dot product between two vectors, are always commutative, can be commutative, not always. The dot product between two vectors are commutative. So that's the basic thing. Okay, so you can also write AB transpose by A transpose and B transpose. That will be equal. So you can write this AB transpose equals to A transpose B transpose, and that is equal. Okay, so these are some of the basic properties that you should need to know for machine learning or deep learning and etc. And I hope that you understood about scalars, vectors, transpose, operations with the matrices, and addition, multiplication, then what is associative, what is commutative. There is something on Hadamard product, it's just like dot product. Okay, so that's the thing, and I hope that we have covered the first page of our notes. Great. So now what we will do, we will talk about the norms, mean the length of the vector or the length of the matrix. How do we take out the length of a vector or a length of a matrix? Okay, so for taking out the length of a vector, so for example, in order to take, you have a vector v 2 3. Okay, you plot it on an xy plane and you get this. Okay, so this is a vector. So how do you take out the length of this vector? Okay, for taking out the length of the vector, or we call this the norm. Okay, rather than length in linear algebra term, we call it a norm of our vector v. Norm of our vector v. Okay, so that indicates the length of our vector v, that is basically equals to L1 norm. I'm taking out the L1 norm. So it's just basically equals to, we have different norm that we'll study. Okay, so here are some of the properties that I've written in the equations. So we have L1 norm as well as L2 norm. So VI. Okay, so absolute value of xi. That's what we do. Okay, so for taking out the norms, we have L1 norm, L2 norm. So we have L2 norm is just Euclidean distance. So what we do in Euclidean distance is just square every element of the matrix and then a squaring root. Let me write the equation for that. So for example, you want to take out the length of a vector v, the norm of a vector v, we sometimes denote as a norm. With L2 norm, we denote this 2 as an L2 norm. The square root of I equals to 1 all the way down to the n xi squared. Okay, so this is just a Euclidean norm. We also have L1 norm where we take out the absolute value of x. Okay, so this is your v L1 norm, and what do? You take out p will be any number of dimensions. Here it is 1. Okay, here it is 1, where we have taken the L1 norm. It just measures the distance from the origin to the x. Okay, so that's the basic L1 norm, that's the basic L2 norm. We also have something called as max norm, which is used to L infinity. Okay, L infinity, where is which measures the it is just, you can see the detail on the book, but it's called the max norm, which is the norm of x or v, norm of v. Approaches infinity, we take out the max, of I, absolute value of xi. Okay, so that's the max norm. So we taken out the length of any vector. Okay, we taken out the length of any vector. Now we taken out the length of any vector. Now how do we take out the length of any matrix? So for taking out, we have something called as Forbinous norm. So for example, you want to take out the length of a matrix A. We write f over here, square root of I and j, I and j squared. Okay, so this is sometimes called the Forbinous norm. Okay, so this is what let's recall the norms are. For taking out the length of a vector or the size of the vector, we have norms. We have some norms, which is L1 norm, L2 norm, max norm, and Forbinous norm. The first three norms are used to measure the length of a vector. The Forbinous norm is used to measure the length of a matrix. Okay, so this is what the thing is. And okay, so you can take out the dot product. Dot product can be written in terms of this x transpose y. We are transposing our x, so this is the dot product where we do the element wise product. Can be written in terms of norm. First of all, we take out the norm of x. L2 norm of x means norm of x times the norm of y. This is L2 norm. The L2 norm. You take out a cosine of theta. Cosine of theta. I hope that you remember TOA in your trigonometry classes. Okay, so you take out the cosine of your theta. Okay, and theta is the angle of between two vectors. So theta is the angle between them. So this is sometimes called, means whatever you map this. Okay, you apply this over here, and this is called the projection P. Okay, and then you P times for taking out the dot. But you don't have to worry about what I'm saying. It's just a little bit advanced orthogonality concept. But over here, what you are doing, you're taking out the dot product in terms of norm. Okay, and theta is the angle between these, and you take out the cosine of that angle. Okay, and I hope that you know about cosine, adjacent over hypotenuse. Okay, so just assume TOA. Okay, so just remember this for trigonometry classes. Okay, great. So we have talked about our norms, and now we will just go to some of the matrices like inverse of a matrix, identity matrix, and etc. So first of all, what is identity matrix? Identity matrix are who does not change a vector after we multiply with that. What is this? So it's just like multiplying with 1. Okay, so you have the identity matrix are where the diagonals are 1, and everywhere we have 0. Oh my god, what I've done over here. So you're going to make a 3 by 3 matrix, 3 by 3 identity matrix. So in diagonal you have this 0 1 0 0 1 0. So in oh my god, over here you should have 1. So the diagonal are all 1 and everywhere we have 0. So that's the identity matrix. So identity matrix are who we multiply. It's just like multiplying with 1. Okay, so if you multiply with any vector, it will does not change that vector. Okay, so that's the identity matrix. So it can be any dimensional I and multiplied with the vector is always resulting in an or the vector that was previously before. Okay, so that's the basic thing about identity matrix. Another term which is more which is a lot we will hear today, which is something called as matrix inverse. Obviously it's not used too much, but if you have heard of in your class 8th, they have talked about the inverse of a matrix. So you take out the inverse of a matrix by A minus superscript minus 1 times A, which is always resulting in your identity matrix. Okay, so that's the basic thing. Okay, so I hope that you remember this in exponents and powers what we do, and it's just but it's not used. If you can see, even I'm not concentrating more on matrix inverse, but you can have a look at Gilbert's triangle video on matrix inverse. He have explained very much good way, so you can have that, but it's not used in the machine learning too much. Okay, so we have talked about our matrix inverse and everything. Now we can write our means if you have heard of system of equations, so we will talk about system of equations soon, but system of equations just like ax equals to b. Okay, ax equals to b. We will see this we will talk about this in detail when we get in the further level. So I thought I'd have talked to you all about system of equation, but it's left. So this is your inverse of matrix. So what is system of equations? So system of equations are this. For example, ax equals to b, where a be the member of a real number with m times n matrix. So it's just a matrix, and b is just b is the member of a real number with m columns. Okay, so that's it. So that is the following, and I hope that you are understanding the system of equations side, that you don't need too much now. Okay, so we have talked about a lot of things in linear algebra. We have talked about addition, we have talked about subtraction. Oh my god, subtraction and addition, these are pretty much simple. You do the same by addition, you do the same by subtraction, and multiplication is the same. And you talked about some of the properties, and I hope that you really understood everything you need to know about linear algebra. Okay, so I think that we are very close to completing this video. So we will close this chapter with this linear algebra with one of the important concept in machine learning which is used today, which is kind of eigenvectors and eigenvalues. I will cover that and end this video. Okay, so first of all, there is something called Eisen decomposition. What do you mean with that? But before that, what I'm going to do is I'm going to take one integer 12. Okay, so you can decompose this 12, this integer, into its prime factors. You can decompose it 12 into its prime factors, which is 2 times 2 times 3. Okay, so these are his prime factors. These are his prime factors. Okay, so the same way you can decompose your matrix, or you can decompose your matrix into its useful properties, and after decomposition you can use its properties and other things. Okay, so it's called Eisen decomposition. Okay, it's called Eisen decomposition, where you decompose your matrix into a different factors. Okay, so it's called Eisen. There are something called as for decomposing, we have into a set of vectors, we have eigenvectors and eigenvalues. Okay, so for decomposition we have eigendecomposition, and to decompose into a set of, after we decompose in so what if we apply the eigendecomposition, we decompose our matrix into a set of vectors which is eigenvector and eigenvalues. These are used a lot in storing, you will hear about in principal component analysis about this, but eigendecomposition is quite easy. For example, you have this 12 and you just 2 by 2 by 3, this is the factors, you decompose your 12 into certain factors. In the same way, eigendecomposition decomposes the matrix into eigenvectors and eigenvalues. So let's see what those are, eigenvectors and eigenvalues. Okay, so but before that, I want to talk about linear transformation. What are linear transformation? What are linear transformation? Linear transformation is just like a function, but it's a function that transforms one vector space to another, following the or respecting the underlying nature of that, linear nature of that, structure of that vector. Okay, so what do I mean with that? So I'm going to write a definition. It's a function t that transforms one vector space to another following the underlying linear, I'm saying a linear nature. If it's not linear, it's no more a linear transformation. Even a small thing, it's not a linear transformation. You can watch for visualization there is 3 blue 1 brown for a linear transformation. Okay, so the function that's transform your one vector x to another one space to another is following the underlying nature, following the underlying structure of each vector space. So for example, you can write your n, you transform your vector to another dimension. Okay, so this is what you do. So for let's take one example. Okay, so you have a linear transformation t equals to ax, sorry, oh my god, t of x equals to ax. So you have, I'm going to talk about 1D linear transformation is just like it's necessary. So you have this and 0 and 1. Okay, so you have this vector, okay, you apply this a is some scalar, now you apply a linear transformation. Now you apply a t of x with the factor, we have taken a as a 3, with the factor of 3 and x is a vector. Okay, so this is a resulting transformed with, so what it will do, it will transform this vector, of 0 1 2 3 by 3, means it maps your interval from 0 to 1 to 0 to 3. Okay, with 3. Okay, so 3 is a factor by which it's scaled. Okay, so this is the linear transformation. Okay, so what are eigenvectors and eigenvalues? So if the new transform vector is just scaled version of the original vector, then the original vector is known as the eigenvector. Okay, so just listen my definition. If the transform vector means this one, if the transform vector is just the scaled version of the original vector, then the original vector is known as eigenvector. Okay, so this is the eigenvector. The factor by which it is scaled is known as eigenvalues, which is denoted by the lambda. Okay, so this is just a definition. I don't want to do the mathematics as of now. You can watch some of the vlogs to see how the mathematics has been done. From this video, I want to give the concept of basic intuitions which are necessary for you to understand ML algorithms. Okay, great. So I hope that you got what are the eigenvectors. Eigenvectors are the one which is the, for example, the transform vector. If the transform vector means this vector is this vector is the scaled version of this original vector, then the original vector is known as the eigenvectors, and the factor by which it is scaled is known as the factor. So it is the scale by 3. So the factor by which is scaled is known as eigenvalues, which is represented by lambda. Okay, which is represented by lambda. Okay, great. So we have covered this, and I hope that you got to know about eigenvectors and eigenvalues in detail. Great. So there is something called as determinant. Is just like determinant are the, you take out the determinant of a matrix, which just maps your vectors to some scalars. Okay, so in simple terms, determinant are the product of all eigenvalues. So what it does, it measures, it measures how much multiplication of a matrix expansion is, and I hope that this does not make sense to you. But in simple terms, determinant, it just maps your matrices to a vectors. It means it's a product, in simple terms, is the product of all your eigenvalues. Great. So we talked a lot about everything you need to know, and please let me know if you want these notes. I prepared a lot. These notes are very useful to me as well. Okay, so from this video I also made my revision as well. So maybe I had done some errata. I will see if I have done some errata. I will surely put in the comment. But we have talked a lot about these all, and I really hope that you enjoyed this video. And now you are able to take that ML001 course. Okay, so you can start watching that ML001 machine learning course if you are new with math. Now you will be able to understand everything over there. Okay, great. So we have spent a lot of time, and I hope that you will like this video. And if my English gone wrong, I have my dictionary. I will surely see in my dictionary. Please be sure to put the English words. I will see in dictionary. So it's my Oxford dictionary. I paid around $10 for this. Okay, great. Thank you for seeing this video. I'll be catching up in the next video. Till then, keep learning, and please be sure that deep learning course is coming with amazing lectures soon. Okay, thank you for seeing this video. I'll be catching up in the next video. Till then, bye bye.